Hi everybody, Captain Al speaking with your month 5 bonus video. We're going to do it on pneumatics and the air conditioning system. We'll start with pneumatics. Each engine takes bleed air from two sections of the engine to provide bleed air to the using components. There's a HP bleed section and an IP bleed section. The IP is the intermediate pressure section of the engine, and the HP is the high pressure bleed section of the engine. In normal thrust conditions, which is in cruise and in climb, pneumatics will be provided from the IP section of the engine through a one-way check valve, which is right here. And during low thrust settings, then the high pressure bleed valve will open, and that air from that section of the engine will supplement the IP air to increase the pressure because the engine is retarded toward idle. So at low thrust settings, you'll have both HP and IP air. At higher thrust settings, which is most of the time, you'll have just IP air. That hot bleed air is fed through a fan air pre-cooler. The fan section of the engine is used to cool that hot bleed air, and then you will have cooled bleed air. It's still warm, but it's not hot. The cooled bleed air is used to provide pneumatic power for the engine starter. It also can be used for the thrust reverser on each engine. For the GE airplanes, the Pratts are hydraulic, but the GE engines are pneumatic. So thrust reversers 1, 2, 3, and 4 will come from the bleed air system, the pneumatic system. On the Salini ice, of course, when the Salini ice valve is open in auto or when you turn it on, then hot bleed air will be used for the cowl to remove any ice buildup. But really, this is still pretty warm air coming out to the Salini ice. You also have the engine bleed air valve for engines 1, 2, 3, and 4. And this will allow the bleed valve to open, and then the bleed air from the engine, from the IP or the HP section, or both, will be allowed to flow through the other using components. So you can see that engines 1, 2, 3, and 4 are basically the same. They all have IP and HP air. They all have air that's supplied to the engine starter, and they all go through a fan air pre-cooler. And again, the thrust reversers are on the G engines are supplied by pneumatics. The Salini ice uses pneumatics to prevent ice from forming in the inlet section of the engine, and that could possibly do damage to fan blades. And then the engine bleed valve would open up in order to supply pneumatics to the hydraulic reservoir in systems 1, 2, 3, and 4. The hydraulic reservoirs will use bleed air to prevent any kind of foaming that could take place in the hydraulic fluid. So it maintains a positive relative pressure to keep the foaming at a minimum. If we go up to the next section, just above that, air is also supplied to the air-driven hydraulic demand pump in systems 1 and 4. You can see here. And that systems 2 and 3, of course, are electric demand pumps, but systems 1 and 4 are air-driven demand pumps. The electric pumps are lighter, more efficient in terms of their weight. But of course, system 2 and 3 doesn't have the high ticket items on it, like landing gear and flaps. So system 1 and 4 use air-driven demand pumps to provide the oomph that's needed to drive those high-using components. In the 747 Classic, they were all air-driven demand pumps, but in the 400 and the Dash 8, they went to supplying electric demand pumps for systems 2 and 3, which helped reduce weight, basically. Pneumatics is also supplied to the left wing anti-ice system and the right wing anti-ice system. The wing anti-ice valves would open either automatically, or we can open them manually if you have the manual switches, and that would allow bleed air to flow into the leading edge devices to supply wing anti-ice. And of course, as we mentioned in the FTD, the wing anti-ice system can be used as a de-icer or anti-icer. The wing anti-ice system is more effective as a de-icer, but you can use it as an anti-icer or a de-icer. And the leading edge, the anti-ice system for the leading edge wing is only effective when the leading edges are retracted. So if the leading edges are extended, all that pneumatic air is just dumping overboard. The left and right wing leading edge flaps are also powered by pneumatics. The inboard, the midspan, and the outboard section. Number 2 here would be the duct pressure sensors to sense the pressure along the duct. If there's any kind of a duct leak, the left and right ducting can be isolated. If the left and right ducting is isolated, then that would prevent the center bleed air duct from receiving air. In the center bleed air duct, you have stuff like the cargo smoke detection that uses sample air through the cargo compartment. Air from the cargo compartment is sampled into the detectors, which use bleed air to then sense if there's smoke or not. The potable water is also pressurized by the center bleed air duct, along with aft cargo heat comes from the center bleed air duct, and the master trim air valve is from the center bleed air duct. So normally the left and right isolation valves are open, and that will allow air from engines 1, 2, 3, and 4 to supply these things. But if for some reason both isolation valves are closed, then you would not get the things that are on the center bleed air duct. The left and right, either one can be isolated in the case if there's a leak in the left system or there's a leak in the right system. Then that isolation valve can be closed and isolate those using components. The APU can also supply air through the center bleed air duct and through the isolation valves to all the using components if the engines are not running. And then, of course, that conditioned air that is cooled by the fan air pre-cooler is also fed to the packs. And again, it's a little bit too hot for the packs to use, but then the packs, their whole job is to convert the air from that hotter air into cooled conditioned air that is then fed to the cabin and to the flight deck and all the zones that we have in the airplane. Looking at the engine bleed air switches, you've got 4 of them. They're alternate action switches. They're normally left in the on position. If you were to turn the engine bleed air switch off, then the PRV, the HP, and the engine bleed valve would all close. When you have the switch on, then that allows the engine bleed valve and the PRV and the HP to open when they open due to system logic. So normally if there's pneumatic air present, then the engine bleed valve will open, and then the HP and PRV would be open as required by system logic. The system fault lights would indicate if there was a bleed air over temperature, bleed air over heat, or if the HP was open when it's been commanded closed, or the PRV is open when it's been commanded closed. Any of those conditions would bring on a system fault light. The APU bleed air valve, when it's in the on position, allows the APU pneumatics to open the valve automatically. Most of these switches are electrically controlled and pneumatically operated. So if there's APU bleed air present, then the APU bleed air valve will open and allow air to flow into the center bleed air duct through the isolation valves to all the using components. And of course, this is a description of all the items that are on the pneumatic panel for your reference. Bleed air again can come from the APU. It can come from ground conditioned air or from carts that can supply air for the starter motor. There's also conditioned air that can be hooked up as well to provide for the packs. which is a lower pressure air, but it's conditioned to go into the mixed manifold. But this is hot bleed air for engine starting if the APU is not operating. So this could be from ground carts. You also have the hot bleed air coming from engines 1 and 2 and 3 and 4. And that air again is cooled from the fan air pre-cooler, and then it's allowed to flow into the ducting, the left and right ducting and the center ducting. 11 would be the pack valves. If the packs are in the normal position and there's pneumatic pressure, the pack valves will open and allow that bleed air into the packs, and then the packs, of course, are going to convert that hot bleed air into a cooler conditioned air, and then that air is fed into the mixed manifold and then taken to the various zones. Number 4 here would be the master trim air valve that allows the master trim air valve to open, and then bleed air can be fed to each of the individual zones. Number 6 here would be the aft cargo heat. When that is on, then hot bleed air could be supplied to the aft cargo section. This is all the hot air that comes into the individual trim air valves for each zone. The packs, of course, will put out pretty consistent air between all the zones, but it looks at the zone that's requiring the coolest air, and the zone that requires the coldest air is kind of the controlling zone. And so it sends its requirement to the packs, and then the packs put out air to satisfy that zone requiring the coolest air. And then all the other zones will be brought up to temperature using these individual trim air valves that will allow the trim air to mix with the conditioned air for those other zones to bring them all up to temperature, because otherwise they would be too cold. This is looking at a passenger airplane, but in the passenger airplane you have 7 zones. You have the flight deck, the upper deck, and zones A through E, A, B, C, D, E. And again, there are, on the passenger airplane, there are 4 recirculation fans, 2 lower, 2 upper. Generally, the air underneath the passenger compartment, that air is fed into the recirc fan in the forward section and the aft section, and then that air is allowed to recirculate back into the overhead area of the airplane to recirculate that air. Normally in cruise flight, all 4 of these recirc fans are operating. In other than cruise flight, it's usually 2 of the 4 recirc fans that are operating. In cruise flight, generally the packs will put out normal flow, but in anything other than cruise, the packs will put out high flow. If you're in cruise flight and you require more conditioned air, you can always turn the pack switch, the high flow switch, to on, and then that will provide more air for ventilation in cruise. Because in cruise the packs do go to more of a normal flow, and again, if you required more air, you could turn the high flow switch on. It used to be more of a factor when smoking was allowed, because then smoke would tend to filter in the airplane, and the high flow switch could be used to remove a lot of that smoke. Of course, we don't have that disgusting problem anymore. You can see here that warm bleed air is fed into the aft cargo compartment. And then there is a temperature control valve that will allow the temperature to be controlled automatically in the aft cargo compartment within a certain range. If the temperature control valve failed, then there is a secondary valve, a overheat shutoff valve, that would control the temperature at a higher temperature. The forward cargo compartment gets its heating from the equipment cooling. So generally the air that is fed from the upper deck area, that air is fed into the E&E compartment and also into the flight deck electrical equipment racks in order to cool the equipment cooling. And then that air that is allowed to flow into that system then exits the system through the inboard exhaust valve into the forward cargo compartment. So we're really utilizing that cooler air that comes in, takes the heat from the equipment, makes it hotter, and then that's being fed into the forward cargo compartment for heating of that compartment. There also is a ground exhaust valve that can be used on the ground, and it works in conjunction with the inboard exhaust valve. They usually work opposite to each other. So the ground exhaust valve might be open and the inboard exhaust valve would be closed, or the ground exhaust valve would be closed and the inboard exhaust valve would be open. And that would simply allow the air to either be ducted overboard or into the forward cargo compartment. And this depends on the ambient temperature outside. Generally in the 45 degrees Fahrenheit is about the cutoff, and in colder temperatures the air will be allowed to flow into the forward compartment. In warmer temperatures the air is allowed to vent overboard. There are fans and valves. You're seeing here the valves, but there's all fans within these systems too that move the air along into the various compartments. There's a smoke override valve that will allow the equipment cooling. If a fan fails or valves fail, then the system can be reconfigured to override, and all the fans and valves will shut down. The smoke override valve will open up, and that air will be allowed to have a reverse flow through that smoke override valve, which will provide differential pressure, and then the air will be drawn kind of in an opposite direction to help cool the equipment cooling if it wasn't required, if it wasn't getting adequate equipment cooling before. In the freighter you have 7 zones as well, but it's the flight deck, the upper deck, and then you have the forward main deck, the aft main deck, and then you have the forward lower lobe and the aft lower lobe compartments in the freighter. Those are considered the 7 zones. But in the passenger airplane, it's the flight deck, upper deck, and zone A through E. And those are the ones that would get the individual trim air control as well. Looking at the air conditioning panel, you've got the 3-pack control selectors, off, norm, A and B. Off is off, the pack valve will be closed. Normal will electrically control the pack valve, but it does take pneumatics to open it. So it's electrically controlled, pneumatically operated. There are 2-pack controllers, A and B. And with a switch in the normal position, it will select A or B on alternating flight bases. But you could select A or you could select B. If you select A and A fails, then it will automatically go to B. If you select B and B fails, it will automatically go to A. If you're in normal, it's going to just switch automatically. And again, in normal operations, it just switches alternating flight basis. Pack reset switch is used if you get a system fault light. A system fault light here would be a pack controller fault or pack overheat. In the passenger airplane, you do have a gasper switch that allows air to flow to each of the individual gaspers at a passenger seat. The high flow switch is normally off, and as we said, the packs normally would be in high flow during climb, during descent, but on cruise flight the packs will go to a more normal flow, and that reduces fuel consumption. And but if you needed high flow, you could always turn that switch on even in cruise, and then the packs will go to high flow. Again, there are 4 recirc fans, 2 lower, 2 upper. And in cruise flight, they're all operating. And other than cruise flight, 2 of the 4 are operating. The aft cargo heat switch allows temperature bleed air into the aft cargo compartment. And again, there'll be a temperature control valve that opens and shuts that controls the temperature range. But if that were to fail, then the temperature overheat shutoff valve can operate. And if it gets to the overheat shutoff valve range, you'll get a temperature light in this switch. The zone reset switch would be for the particular zones. A system fault light there could be a zone duct overheat, a zone controller fault, or if the master trim air valve is closed. The passenger temperature selector will be in the range of C to W. The range here for a passenger airplane would be 65 to 85. And in the freighter, that range, I think, is, it wouldn't be a passenger temperature selector. I think in the freighter, it's like 40 to 85. And the flight deck also has 65 to 85 degrees Fahrenheit. Yeah, you can read it kind of down here too. 18 Celsius to 29 for those of you who like Celsius. And the passenger temperature selector will set the master temperature for all of the zones. And then the flight attendants do have some control over that master temperature selector from their controller down at door 2 left. And they can select plus or minus 10 degrees within that range of 65 to 85 for each individual zone. So they kind of do have some control over the heating and the cooling of those individual zones downstairs in a passenger airplane. If the flight deck automatic system were to fail, we do have a manual system. When you go to manual, then you'll be controlling the valve automatically by toggling between C and W. It's spring-loaded to the manual position, but you can open it to a colder temperature or a warmer temperature. In alternate for the passenger, usually it just goes to a constant 75 degrees. So there's a lot more with the pneumatics and the air conditioning. If you're interested, you can read it in the FCOM in those sections. I'm just kind of going over the major highlights of the system. Let's take a look at the questions for pneumatics. Number 1, how can a low pressure condition in the left or right duct be identified? The primary method is through the ICAS message. You're going to get an ICAS message for a left or right duct leak. You also may notice a differential in readings of the duct pressure between the left and the right, which is found on the primary ICAS, at the bottom of the primary ICAS, or on the ECS synoptic. Number 2, what conditions cause the ICAS advisory message bleed isolation to be displayed? This would be a disagreement between the switch position and the valve indication. So if you went to close the isolation valve and the valve light stayed illuminated and you got the ICAS message bleed isolation, it would indicate you're trying to close the isolation valve, but it's still open. It's a disagreement. Number 3, what happens when the left and right isolation valves are closed? This will isolate both the left and the right ducting, and it will also isolate the center bleed duct system. And so those items that are on the center bleed duct system would be lost. What source normally supplies engine bleed air during high power settings? This would be the IP section, or the intermediate pressure section of the engine. Number 5, what source normally supplies engine bleed air during descent and other low power setting operations? This would be the HP valve would open, and the high pressure section of the engine would provide the bleed air during the low power settings. And number 6, what systems use bleed air for normal operation? This would be air conditioning, pressurization, wing and engine anti-ice. It's used for engine start. As we discussed, the leading edge flaps would use pneumatics. Aft cargo heat comes from the center bleed duct. Cargo smoke detection comes from the center bleed duct. Hydraulic reservoir pressurization to prevent foaming. The potable water tank pressurization is supplied by the center bleed duct. You have air-driven hydraulic demand pumps in systems 1 and 4, and the thrust reversers on the GE engines. Number 7, where is pneumatic duct pressure displayed? As we talked about earlier, it's displayed on primary ICAS at the bottom. It may or may not be, depending on what page you have selected. There are certain pages that will bring up the duct pressure, like if you have the secondary engine display on, then the duct pressure will show up. You can also get it by going to the ECS synoptic, and you would see it there as well. Number 8, when is the ICAS advisory message bleed HP engine displayed? This message would be displayed if the HP bleed valve had failed closed. You would get that bleed HP engine message. Let's look at the air conditioning questions. Number 1, how's the master temperature set? It's set by the master temperature selector on the air conditioning panel. And as we discussed, the master temperature for the passenger airplane goes between 65 to 85 degrees Fahrenheit. And you can set the master temperature with that selector. Or you can set in a freighter like the main deck temperature, and that range is a little bit wider at, I think it's 40 to 85. And number 2, what does the selecting override on the equipment cooling selector do? This will disable all the fans, all the valves will close, the smoke override valve will open up, and then differential pressure will create a reverse airflow that will lead to a reverse flow of air through the equipment cooling racks in order to keep them cool. Number 3, why is the aft cargo heat switch left off until after engine start? Primarily to allow an increase in bleed air for the engines to start. So we don't want to be taking air from the engines during start by having the aft cargo heat switch on, since it does use bleed air. Number 4, when does the zone system fault light illuminate? The zone system fault light illuminates for a zone duct overheat, a zone controller fault, if the master trim air valve is closed with pack air still present, or if the master trim air valve has failed to close, or if the trim air switch is off. These would all cause the zone system fault light to illuminate, and that's right over here. Number 5, how much air pressure is required for the pack valve to operate? I don't know if there is a minimum pressure. I mean, it's electrically controlled, pneumatically operated, so as long as you have bleed pressure, that will open the valve and allow air to flow then through the pack valve. And that completes the questions on pneumatics and air conditioning.